Alright, so we are on electron configurations part 2 now. Let's go ahead and begin. So it says number 6, examine the orbitals in electron configurations in model 2. This is model 2. Match each symbol below with its meaning. Okay, so my box is a pair of electrons. Oh, actually, let's go here. Number 2, a pair of electrons with opposite spins. Okay, so that makes sense. I'm going to put 2 right here. That was an easy one. So that means that this must represent an electron. So that's a single electron. Okay, atomic orbital, region of space where an electron is likely to be found. Huh, okay, so, and then this one says sublevel. Oh, you guys can't even see. This one says sublevel, a set of orbitals having equivalent energy. So this must be one orbital, this must be a set of orbitals. So this must be an atomic orbital. So 1, 2, 3, that's an atomic orbital. And this must be a sublevel, a set of orbitals. 1, 2, 3. So I'm going to go ahead and put right there. Okay, so that leaves this for an electron configuration. So this is V, right there. Okay, so now it says, consider the orbital diagram for oxygen in model 2. Let me get my pen real quick. Sorry guys, I left my pen over there. Okay, so let's see. The orbital for oxygen is this one right here. So go away. Okay, so consider the orbital diagram for oxygen model 2. How many electrons are present in the orbital diagram? So, for oxygen, for this one right here, I can do this 2 ways. I'm going to go ahead and just count. I know that a single electron is an arrow, so I'm going to go ahead and go just 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to go ahead and write 8 right here. Based on its position in the periodic table, explain how you know that your answer to part A is the correct number of electrons for oxygen. Okay, well, looking at my periodic table, oxygen is right. Oh my gosh, I'm holding this iPad right here. And oxygen, we know this is our atomic number right here. And it goes 1, 2, 3, 4, 5, 6, 7, 8. That's the number of protons there are. And because we know, unless I tell you, we always have a neutral atom, 8 protons means 8 electrons. So that makes sense. Oh, gotta slide in just more. Okay, good plans. Alright, here we go. So I'm going to say, looking at the periodic table, my hands are so cold right now, you guys. This is when my classroom was freezing. The heater doesn't work. Looking at the periodic table, oxygen has 8 protons. And therefore, I'm going to use these 3 dots for therefore, and therefore 8 electrons because it's neutral. That says neutral. Oh my goodness, my hands are literally so cold. Okay, number 8. It says examine the orbital diagrams in electron configurations in model 2. Using the following electron configuration, underline the energy levels. Okay, so my energy levels, 1, 2, 2. Okay, so it looks like, just like the levels of floors that we had, I think that those are also my energy levels. Okay, so that means that I'm going to go ahead and underline the energy levels. These are my energy levels. Energy levels. Circle the sublevels, and the sublevels are each orbital that has an equivalent energy. Okay, so it's these things right here. So I'm gonna go, so I have the S's, the P's, kind of like the sunny in the pink room. Okay, so those are the S's and the P's. I'm gonna circle those, so circle, circle, circle. Draw a box around the number of electrons. So electrons is gonna be 2, 4, 8. Oh, okay, so there's 8 electrons. So these must be the same atom. And if we look right here for oxygen, yeah, that's what we have right there. Okay. All right, so number 9, the 2s and 2p sublevels are very close in energy, as are the 3s and 3p sublevels. What does that mean? Okay, so this is the 2s and the 2p, so they're very close in energy level. So if this is one energy, I guess I'll do it right here. If this is one energy level going this way, and this is a second energy level going this way, and this is a third energy level going this way, you can see that, well, there's nothing next to 1, but 2, the 2s and 2p, they're really close to each other, but it looks like this one is a little bit higher than this one. This one's a little higher than this one. Explain how the orbital diagram for sodium confirms that the 3s sublevel is lower in energy than the 3p sublevel. Well, you can see that because the 3s one right here is literally drawn lower on the diagram than the 3p. So the 3s is lower on the diagram than the 3p. Okay, so 3s is drawn, I'll say drawn, lower than the 3p. So that just means that these have more energy up here, increasing energy. So the electrons that are up here have more energy than these ones, which have more energy than these ones. Okay. Number 10, the lowest potential energy arrangement of electrons in an atom is called the ground state. We've heard this word before. So the lowest potential energy. What the heck is potential energy? Okay, so if I had a bowling ball, if I'm standing here, oh, Miss Moore, and a bowling ball was chilling, I guess I'm standing right here on the ground. The bowling ball is on the ground right there. It's chilling. If I was to hold the bowling ball up here, it has the potential to have more energy because if it drops, okay, when it drops to the floor, it is going to lose energy. So it has a higher potential energy here, a lower potential for energy here, because as soon as I let this go, all of the energy that was being stored in me picking it up is actually converted into kinetic energy as it moves down. So what do you need to know? Potential energy increases the higher you hold something up in the air. The higher you hold something up in the air. And if we think about the law of conservation of mass, that we talked about, you can't destroy or create mass, everything's conserved. The same thing happens with energy. We have a law of conservation of energy. There was honestly a law of conservation for tons of stuff. But for energy, the same exact thing applies. You can't gain or lose energy in the system. It's only conserved. It only changes from one form to another. So up here, I have all potential energy and I have no kinetic energy. Kinetic energy is moving. And then as soon as I let it go, that energy changes from potential, 0 now, and right before it hits the floor to all kinetic energy. So if you don't understand that, that's totally okay. But what you need to know is that at the ground state, it is the lowest energy. Ground state electron configurations can be predicted by a strict set of rules known as the off-bow principles. Pronounced off and then bow, like when you bow for someone. Examine the diagrams in Model 2 and the statements below to determine which ones are correct. Okay, so based on where a single electron is placed, the lower potential energy electron in an atom is found in the blank sublevel. So basically, which one fills up first? Okay, well it looks like the lowest ones are going to be in the 1s. Okay, and then they fill up in the 2, and then the 2s 2p. Over here we've got the 1s filled up, the 2s, the 2p, and then the 3. And then over here, it goes from 3s to 3p. Okay, so it looks like it goes from 1s to 2s to 2p to 3s to 3p. Let's look at the question again. I forgot what I said. Based on where a single electron is placed, The lowest potential energy electron in an atom is found in the, oh, that's easy, the 1s. You're always going to fill up the 1s first. Electrons will occupy p orbitals. This is like the pink room. Only after the previous s orbital is half full. No way, I don't see any p orbitals that have half full s orbitals, so it can't be that one. The previous s orbital is completely full. Okay, yeah, so any p orbitals that are filled, the s orbital is completely filled. S orbital completely filled. Okay, maybe that one, the s orbital is empty, definitely not. Okay, so you have to fill up. You first start off by filling in right here, and then you have to fill this up completely before you go to this one. Okay. Electrons can begin to occupy energy levels with the next highest integer designation. For example, 1 versus 2 versus 1, 3 versus 2, only after blank on the energy level below are occupied. Okay, what does that even mean? So what that's saying is, if I am, it's saying that if this is level 1, and this is level 2, and this is level 3, it's saying electrons can begin to occupy the next energy level only when, well, it looks like you could only go to the next energy level, like over here, when everything below it is filled. Yeah. Right? So everything here is filled, and then they went up here. Everything was here is filled, and they went up there. They filled this, then they go up here. Okay, so only after half the orbitals on the energy level below are filled? No. All the orbitals. At least one? No. All of the orbitals, all of these boxes, box, all of those orbitals have to be filled before we can go on to the next one. Okay. Boop, 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 boop. Dang, this is a long video, Miss Moore. Okay. The Pauli exclusion principle describes the restriction of the placement of electrons into the same orbital. Whoa, what does that even mean? So it has to do with when you can put electrons in the boxes. The Pauli exclusion principle can be expressed as if 2 electrons occupy the same orbital, they must have blank. Okay, so the same spin or opposite spin. Okay, well, you look at these, and this is an electron going this way, and that's an electron going that way. Ooh, and look, it says a pair of electrons with opposite spins. Okay, so it must be opposite spins. This is called the Pauli exclusion principle. Whatever the heck that means. Pauli. I don't know if y'all have Polly Pockets, but okay. So we had the off-bow principle. Off-bow, it sounds regal. Which tells us that you must fill up the orbitals starting at the bottom energy level and then moving your way up first. And then this one says that when you draw in the arrows, they have to go up. They have to have opposite spins, going one direction and the other direction. Okay. Hund's rule describes how electrons are distributed among the orbitals of the same sublevel when there is more than one way to distribute them. Hund's level consists of 2 important ideas. Based on Model 2, circle the correct one. Okay, so electrons will pair up in an orbital only when, well, it looks like, okay, so it looks like they all go one direction first, and then once they all have one direction in, then they go down the other way. Okay, so electrons pair up in an orbital only when there is an even number of electrons in the sublevel. I don't think that has to do with it. All orbitals in the same sublevel have 1 electron. Oh, okay, yeah. So all of my orbitals, for example, right here, orbital, this is an orbital, this is an orbital, and this is an orbital. They all have 1 electron. So then and only then, for example, right here, would they come down and put another one in like that. Okay. When single electrons occupy different orbitals at the same sublevel, they all have the same spin, they all have different, oh, that's easy. They all are going the opposite direction, right? Up and down, and all here, up. Okay, so, oh, sorry, when a single electron occupies different orbitals, they all have the same spin. Okay, so when a single electron occupies all the orbitals, they all have the same spin. They all have the same. That's this one. Okay. Number 13. For each of the symbols below, for Model 2, provide the name and description of the analogous component that we use in the boarding house. Okay, so let's go back to our first picture, our first one here. Okay, so let's see. This was definitely the sunny room for sure. Okay, and this was definitely the pink room. Pink. One electron was the same thing as one border for sure. And 2 electrons was just 2 borders, or 2 people. Now, we haven't really talked about this too much, but this is the same thing as my manager's code. And we call it, in real life, an electron configuration. Okay. You can skip letter B, and we're going to skip letter C. Oh, actually, you know what? If you did letter B, what characteristic of electrons is not well represented by the boarding house? Well, I will say, my hands are so cold, that if you look at both of these, the difference is that this is level 1, this is level 2, and that's level 3. The only difference is that level 2, you can see that there's a difference in energies. It's almost like there should be like a step up to like a level 2A on over here. And again, this is level 3, but it's almost like there's a little step up there. So I think what's not represented well is that is the energy levels. Energy level difference between 2s and 2p and 3s and 3p. All right, so last page here. Woo, I'm running stretch here. Below are 3 answers generated by students in responses to the prompt. Provide an orbital energy level diagram for the ground state of a nitrogen atom. And so we haven't talked about the excited state yet. All we've talked about is ground state, which is when the electrons are where they're supposed to be. In each case, indicate whether the answer is right or wrong, and if it is wrong, explain the error. Okay. Let's take a look at this one. Let's see. We fill up the 1s first. Good. Oh, we are supposed to fill up the 2s first. Let me go ahead and look at my rules. Okay, well, the off-bow principle says, based on, it says that, the off-bow says that we should put all the orbitals, we should be filling up the 1s orbitals first. So they're messing up the off-bow principle, because what should happen is there should be an arrow right here. So I'm going to say off, I can't spell this, off-bow principle is messed up. And that means that they should have put one here first, not there. Okay, let's see. The Pauli exclusion principle, that has to do with the opposite spin, so we're good. And then Hund's rule is that all orbitals in the same suborbital have 1 electron. Electrons will pair up in an orbital when, okay, so yeah, that doesn't have to do with it. Okay, so just messing up off-bow's principle, which states that electrons will occupy, so electrons must fill up lower energy levels first. So they should be filling up the 2s first, not the 2, and before they go to the 2p. Okay, let's look at this one. Okay, this is filled up, and then this. Nice. Okay, so my off-bow principle is good to go. My Pauli exclusion principle talks about how they're supposed to have opposite spins. Okay, yes, yes, yes. All right, 1, 2, 3. And my Hund's rule says that when a single electron occupies different orbitals like this, that they all have to have the same spin. Okay, so this looks good to me. No mistakes. Sweet. Okay. And let's take a look at this one. Okay, so first the 1s and the 2s and the 2p, so off-balance principle is not an issue. Do they all have opposite spins? Yes. Okay, but let's take a look at Hund's rule. Hund's rule says when a single electron occupies different orbitals of the same electron, they all have the same spin. Oh, actually, you know what? I think that they did mess up something. Let's look at, I'm trying to see if I can find it on here. Oh, that's what I'm looking for. He did mess up the off-balance principle because I was looking for the right words for you guys. Electrons can begin to occupy energy levels with the next highest integer only after all of the orbitals on the energy level below are occupied. Oh, no, that's not right. That's not right. Let's see. Pauli exclusion principle describes the restrictions on the placement of electrons into the same orbital. The Pauli exclusion principle can be expressed as if two electrons occupy the same orbital, they must have opposite spins. Okay, so that one is good. They do. So yeah, it is the Hund's rule. Let me go ahead and read this more slowly. Electrons will pair up in an orbital only when, oh, there it is, all the orbitals in the same same sublevel have one electron. That's the words I'm looking for. So this guy should not be right there. Rather, he should be right here. And that's Hund's rule. And I'll go ahead and restate it for you guys. Electrons only pair up when all the orbitals in that sublevel have one electron. Okay, and if I go back over here, the way that this one should look is I should get rid of that one and I should put it right there, and it should be opposite direction. Okay, whew, that was a little tough. Okay, so last one, complete the ground state orbital energy level diagrams and write the corresponding electron configurations for sulfur, silicon, and neon. Okay, so first, before I do anything, I'm gonna go take a look and figure out what the heck sulfur, silicon, and neon. How many protons? Sulfur, silicon, and neon. Okay, well, sulfur is right there, 16. So I'm just gonna put a little note right here, 16. Silicon is 14. 14. I'm sorry, I'm holding my giant iPad. That's my sister's. And neon, there it is 10. 10. And if you're wondering what that noise is, my room is literally freezing. So I have Mr. Boygan brought in one of my friends brought in an oil heating furnace thing. So bubbling noise is actually oil being heated up to heat you guys up. Okay. So let's go ahead and do this. So 16 electrons, 14 electrons, and 10 electrons. So you're going to see that there's a pattern here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and how do I draw my electron configuration for this? We are going to go, so in the 1s, there's 2. In the 2s, there's 2. In my 2p, there's 6. In my 3s, there's 2. In my 3p, I've got 1, 2, 3, 4. My 3p, I've got 4. Okay, let's do silicon. So again, we start on the lowest energy level, and we have to have opposite spins. 1, 2, 3, 4. Okay, and we have to fill up all of these rows first before we can go back through and fill them up. So I'm at 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So let's go ahead and I'll just draw a line here. Do our electron configuration. So in the 1s I have 2. In my 2s I have 2. In my 2p I have 6. In my 3s I have 2. In my 3p I have only 2. Okay, I'm running out of space here. Okay, so for neon, let's go ahead and do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in my 1s I have 2. In my 2s I have 2. In my 2p I have 6. Boom, done.